And we'll begin with a question that someone DM. So as usual, feel free to DM me the question. Okay, even if it's not really the topic that we're discussing, because I know, the best way to study is also to do your own revision, make sure everything is okay. It's probably pretty okay to ask, and then we can also do a quick flashback to May, June 09, paper 4. Of course, in the year 2009, there's only one paper 4, no variant. That time, not that many people do A-levels. You know what's the funny thing? I just noticed that it's been 18 years since I sat for my A-levels or my Form 6. 18 years, half my life, half a lifetime ago. Feel so old. Okay, age is a number. All right. 904. We're looking at the capacitor question, so this is number 6. If it loads, when it loads. So if you want link to the paper, it's in the chat. Probably also in your handouts. But let's look at question 6. Just look at this paper. It's summer 09. Oh, June 18. And also summer 09. Okay. So we'll do this one first, summer 09, question 6. I think in my collection, I didn't include all the questions simply because older questions is a bit repetitive. But here we have the usual horseshoe magnet. Let me screenshot. Okay, this is question 6. So this one is sort of related to what we've been doing for the past weeks. Okay, and what we have is the regular setup of the current balance. Just bear in mind that here later on they ask you in part C, what happens when we apply direct current? Okay, so let's do it one by one first. In this horseshoe magnet, it says here that the parameters are, you have the length of wire between the pole as 4.4 cm. Direct current of 2.6 ampere is passed through the wire in the direction from X to Y. And the reading of the top pen balance increases by 2.3 G. So when you see this, you should just ask yourself, why increase? Why did the reading increase? So if you've ever measured anything, if you tekan, you press downwards, this will cause the balance reading to increase. So this is the normal force between the magnet and also the surface of the top pen balance. But what you need to know is just that this extra force is what causes the change in weight or change in mass, which is energy. So it's a bit like this one is pulling down. So from Newton's third law, the force on the wire must be upwards. This also will be delta W. So if you are labeling, it could be helpful for your brain to know that this is the force of magnet on wire. And this is the force of wire on magnet, pushing the magnet down. So if you weigh a durian and you push it down, then the weighing machine reading will be more, because this is your balance reading, the change in your balance reading. So the first part is you are given the current and it flows from X to Y. So this is your 2.6 ampere. And you are asked to decide or state and explain the polarity of pole P. So I roughly explain why increase already lah. Okay, but if they ask you to decide whether this is north or south pole, then we have to start with why there is an increase in the first place. Okay, so start with this one. You can say that the balance reading increases. So this means that there is a downward force on the magnet. So this is the first mark. We talk about the fact that there is a downward force. Second point, if there's a downward force in the magnet from Newton's third law, there is an upward reaction force on the wire. Using my left hand, or Fleming's left hand, pole P is, okay, now to decide north or south, take out your left hand and do the whole exercise again. FBI, your middle finger, FBI, middle finger, must point from X to Y. So your middle finger should point away from, towards the screen, away from your face. Okay? And then your force is actually upwards because your force on the wire is upwards. So force on the wire is upwards, middle finger pointing away from you. If you're using your left hand, your index finger will be pointing towards the left. So this is the direction of your magnetic field, B. So this is B, this is I, and this one here is your F. Okay, so the pole P, magnetic pole goes from north to south, like Negara Penjajah, not going down to south, right? Okay, across the equator, especially Europe down to Africa, north to south. So this pole P is not polar. So using Fleming's left-hand rule, pole P is north. 3 marks, one point each. So it's quite standard. It's just that I could change the reading. So I could say the reading decreased, then the explanation will be flipped. Okay, I'm just going to leave this here. We're going to move on to part 2. Part 2 is some calculation. You are asked to calculate the magnetic flux density between the poles. So to find the magnetic flux density between the poles, you are asked to find B. So we know that the change in weight is equal to the change in mg, which also happens to be equal to the magnetic force. So the weight or the mass changed by 2.3 grams. So I'll put 2.3 times 10 to the power of -3 must convert to kg. Because why? Your G, you're going to use 9.81. So convert to kg. Magnetic force is our good old BIL. Okay, so we're looking for B. Do we have the current? Got that here. 2.6. And we have the length of the wire inside the pole, 4.4 cm. So it's just fill in the blank, press calculator, get answer. This is 3 marks. So last time, the marks are very generous. Now, not so much. Oh, by the way, later I will show you the grade threshold and I will react to it. Okay, please don't use G as 10, by the way. So this one will be 0.20 Tesla. It's a kind but firm reminder that all your answers should be expressed in 2SF or 3SF. All right. So the question here is now I want to replace the 2.6 ampere direct current is replaced by a low frequency sinusoidal current of mean square value 2.6 ampere. Okay, so I'm going to draw the current and compare them. So let's say this is I and this is T. For the original one, you have 2.6, and then it's 2.6 all the way. This is direct current. No problem lah. This one we know the reading will change by 2.3 grams, and then it will just stay there until you turn off the switch. Okay, but right now I replace with a sinusoidal current. So I'm going to draw a sinusoidal current. RMS value is 2.6 ampere. So if you remember last time in your Form 5, your IRMS is equal to peak over √2. So this will be 2.6 times √2 will be the peak or the maximum current. All right. Later when we do alternating current, I will prove the equation for you now. But if you are interested, you can go and watch the proof. It's already recorded on the YouTube channel. All right. So right now, if I calculate this, 2.6 times √2, this will give me 3.6. Peak current is 3.67. I'm going to use 3.7 now. I follow their SF. They use 2, I use 2. So it's going to be somewhere up here, 3.7. So you get a sinusoidal current like this. Okay. Where the peak voltage is 3.7 and down here is negative 3.7. Okay. All right. So of course, the change in reading is no longer this 2.3 gram. What I know now is when current is 2.6 ampere, the change in mass is 2.3 gram. It's an increase, right? Increase. So now I don't really care about 2.6 anymore because it's not my maximum value. But what should I care about? I should think about the peak values, this 3.7. So the next question would be, if this is 3.7 ampere, what is this change in mass? And then you may be wondering, teacher, is it directly proportional? Can I use ratio? You always say ratio is my best friend. Well, before you can use ratio, you try to find the equation that relate these two first, just to make sure it is linear and you don't have a square or exponent hiding behind somewhere. Okay. So in this case, I recall normally this part, right? You can check your calculation one. See this? Change in mg is BIL. So I'm going to use this. Since change in mg is equal to BIL, G is constant. We still use the same horseshoe magnet, and the length of the wire is constant. So I can say that the change in mass is proportional to current. Constant, constant, constant. If cannot, you substitute again also can. Because you already have B, you have L 4.4 cm, you have B 0.2 Tesla, we calculated just now. I, you put in 3.7, no? And then you find delta M. Or I can just use ratio. So remember from here to here, we times √2. There, 3.7 ampere is √2. That's why sometimes the mark scheme just bypass all of this and they just time √2 and then student is very confused. Okay. If you don't want, you can also write like that. 2.6 over 3.7 is equal to 2.3 over the new change in mass. You want to find the new change in mass. This mark delta. Okay, I will just take 2.3 times √2. And this will give me 3.25 or 3.3. Is it 3.2? 3.25. I put 25. 25 neither here nor there. So this one is 3.25 grams. So I expect a change of 3.25. balance reading changes by 3.25. Next question, increase or decrease this balance reading? Let's say I copy this graph and draw down here. The balance readings change by 3.25. If let's say I draw a graph, again the same graph, of a change in mass against time, for the direct current is plus 2.3 gram, like that. If I change direction, then it will be minus 2.3 gram. But for alternating current, we keep changing direction, which means the direction of the force on the magnet, the horseshoe magnet, will also change. So this means we will get something like this. It's the same graph. I'm tempted to just copy over. Okay, so here it will be increased by 3.25 gram. And here it would be decreased by 3.25 gram. And what is the question asking us for? Variation in reading. How much will the reading change? If the reading kadang-kadang increase 3.25, kadang-kadang decrease 3.25, then what's the total change? Sometimes I go up, sometimes I come down. So my total variation will be 3.25 plus 3.25, or 3.25 times 2, which is 6.5 gram. That is life, right? Sometimes we go up, sometimes we go down. Okay. Let me know if you have any questions regarding the AC. So this is for current balance. What if you have two parallel wires? Not sure if I've discussed this with you, but let's say I put I1 and I2. And maybe, so this is I and T. This is my I1. And this is my I2. How would the force change? The force, because they are always in the same direction, so same direction will attract. Or you can use the whole left-hand rule. Your magnetic field disturb my current, my magnetic field disturb your current story. But same, they attract. But I just want the magnitude of the force. I don't really care about this one. So I think we discussed this before. So the points that I definitely know is when there's no current, there's no force. So I'm going to plot these points first. The other arrows, the other force. No current, no force. No current, no force. Okay. Maximum current, maximum force. So you sort of like get something, you get something like this. But the force is always attractive. Because when we flip to the second cycle, I1 is like this. I2 is like this. But they are still attractive. You can use this to, get a girlfriend or boyfriend, profess your love. My love for you is like alternating current in parallel wires. Whether we go up or we go down, I'm still attracted. Or non-near. Can also physics pickup lines. But it's the same. Okay? So it's a modulus. You flip to the positive. In this case, we don't modulus it because if the current change direction, then the direction of the force will change because it's only one force. Okay, it's not changing both, we're changing only one thing. Yeah, you go like, imagine if you are like the lame jokes and your couple, your partner also same kind of lameness. That's the best lah. Life is hard, we just laugh. And then we do our best. Okay. We're gonna continue now. Recently, my OneNote is server cacat, so hopefully today is okay. This morning was also a bit cacat. All right, we're gonna, okay, last class, we talked about the magnetic force on a moving charge, okay? And the important thing that we're going to continue on is this magnetic force can be calculated using the equation dqv sine theta. Okay, still use your Fleming's left hand to find the direction of force. Right hand, kita simpan, we keep for induction. Okay, that's me lah. If you want to use right hand for this one, also can. Right hand for negative charge, left hand for positive charge. I don't like to do that. So I always refer to the direction of current. Positive charge will follow current, negative charge go against current. So we know two things will happen. Number one, if I put a moving charge inside a magnetic field, this charge will actually move in a circle. Because this force, this magnetic force must always be 90 degree FBI. F and I is always 90 degree. And because it's always 90 degree, this charge will kind of rotate in a circle. So magnetic force is equal to centripetal force. And from here, we can tell that the radius of deflection depends on either the mass or the charge. And we kind of like put this in a spectrometer to study isotopes and radioactive particles. Then we think to ourselves, is there a way so to adjust so that the velocity is same? Because there's a V here, and I don't want this value of V to disturb my arc. The only thing I want to affect the radius is either the mass of the particle or the charge of the particle. So what do? I introduce a second field, which is electric field, to imbang balik, okay, to balance back the magnetic force. So if these two happen to be equal, magnetic force happen to be equal to electric force, then the charged particle will be able to travel out with no block. I mean, it will just be able to travel in a straight line. We call this undeflected or undeviated path. So if you equate these two, you will get velocity is E over B. So I can adjust E and B easily to make sure that I only get the charge of one velocity to pass through. So we sort of call this the velocity selected. All right. So that's where we stop that day. And we're going to continue from here. Today, we will look at not just this part, but also the Hall effect and hopefully be able to try a paper 5 question regarding the Hall probe. Okay, let me open up the topicals first. I can correct soalan. Okay. Okay, the Hall probe is here. Okay, and the Hall effect and the Hall probe is basically using a phenomena that we can see to design a probe. And the role of this probe is to measure magnetic field, or rather measure the value of B. So I'll write the full name. To measure magnetic flux density. B. Yeah. This is the purpose of this. But what is the Hall effect? Is some dude lah, Robert Hall, I think. Robert. Not sure what his name is, but the Hall dude is just a guy who discovered this while studying his PhD. Yeah. Edwin Hall discovered the Hall effect while he was working on his doctoral degree. 18 years before the electrons was discovered. So actually, right, this era of late 1800 to early 1900 is the era of science. There were a lot of discoveries that happened during that time. So if you happen to be a scientist during that time, Most likely the thing that you discover is a new thing, and then you get to call it your name now if you want to. Right. But what is Hall effect? Let's see. First things first, I got this slice of thing that I draw it out, and I'm going to use a semiconductor. So it's time to revisit Form 5 star. What is a semiconductor? Do you remember that there are two types of semiconductor? N-type and P-type. And they go through this process called doping. Remember or not? We're not going to go into too much detail. Hiya, you know your transistor, the nightmare of many Form 5 students. PNP transistor, NPN transistor. Remember this one or not? Do you remember this? Somewhere got something like that. Then we say, oh, transistor is a switch, but actually you also don't really know why is it a switch. There. We're not going to talk about transistor. Actually, transistor is just, if the charade okay, the switch on. The charade not okay, the switch off. That's all. There's a certain condition. That's the idea of a transistor. But we're going to rewind back and just focus on the semiconductor. So before we start drawing here, I need you to choose whether you want N-type semiconductor. N-type here is negative, right? So the majority charge carrier, let me draw here. Where should I draw? No, it's no. We're going to choose a type of semiconductor for our discussion. So we can either choose the N-type semiconductor, where the majority charge carrier is electron, or the P-type, where the majority charge carrier is the proton. I call this MCCR. I write the whole thing. Which one you want? Proton or electron? Positive charge. Actually, it's not proton. It's actually holes. Holes. Okay, please choose. Select your own adventure. Select your semiconductor. You want N-type or you want P-type? Positively charged holes, negatively charged electrons. Which one you want? You want holes. Okay, let's do holes then. I do holes, you do electron, okay? All right, we have current. All right, so our current is traveling in this side. So this thing is 3D. You got to imagine this like a boxer. Okay, so current is flowing in this way. And we know that the majority charge carrier is holes. So I will call this a P-type semiconductor. So where should I draw? P-type. So this means the positively charged hole will travel in the same direction as your current, because current is the direction of positive charge. So you imagine there's many positive charge sort of like drifting in from this face CDPQ towards this face FESR, because the current is flowing. So the electron, the hole is just traveling like that, minding its own business. And then I turn on the magnetic field. Magnetic field. Turn on this B to disturb the holes. So right now, I have the condition for magnetic force. Number one, I have magnetic field. Number two, I have moving charge. Okay, you tell me, where's the direction of the force? Is it pointed? Or you use the letter and name a face for me. Name a side. Where will the force act? Will it act towards CFSP? Will it act towards DERQ? Will it turn down SRQP? Will it turn up? Where do you think it will go? Use left hand. Use left hand. Give me 4 alphabets to show the face. left, right, up, down. Left. Correct. Very good. The direction of the force will be in this side. Magnetic force. So if you do FBI, B is pointing downwards. Your index finger pointing downwards. Stick out your middle finger. Don't point your middle finger towards you. Point away. The middle finger must point away from you. Your index finger is pointing downwards. So your thumb is going here. CFPS. Okay lah, good enough. June. So this phase is where all the positive charge will go and park here. All the positive will be like, yo, bro, we got the force to push us here. Let's go. So all the positive charge here. Now, this is a generally neutral piece of material. If all the positive charge is pushed to one side, what happens to the other side here? All the positive charge go one side already. So then the other side, the electron is like, yo, bro, where you go? Why you all go there? So all the electrons are sort of stuck here, or the negative charge is here. Does this make sense? So they'll just fly towards here. You know, they all go here, making the other side negative. But sure, if this blue color side is negative, wouldn't it also attract the positive charge? Because, you know, positive holes, negative phase, you're right. So this is an electric force. So two things will happen. Number one side, I have all the positive charge. On the other side, I have all the negative charge. If I install a voltmeter here, I will be able to measure a small potential difference. Sensitive voltmeter here. So this voltmeter will be able to measure the voltage or the potential difference. This is known as Hall voltage. Oftentimes, we will give the symbol VH. Teacher, are you saying that this dude just take a semiconductor, stick it in the magnetic field and the electric field, and then he's able to measure the Hall voltage and he can explain what is going on, and tada, he gets a PhD? Pretty much lah. Pretty much. There's a little bit more. Of course, there's more to that, but that's the main idea. Good. If you understand this, good job. Your brain is pretty much on par as a PhD student. So big brain stuff. Anyway, this one will be deflected. This one will be here. Do you think the Hall voltage reading will increase because more and more electrons will go one side, more and more positive charge will go the other side? But eventually, after increasing, it will plateau against time. And actually, this time is very short. So the Hall voltage actually plateaus to a maximum value. Why does it plateau though? Because when it plateaus, it means that the positive charge no longer goes towards the yellow color side. What makes it plateau? What do you think causes it to increase to a maximum value, and then after that it will stay the same? What do you think? Why? Look at the forces. Because FB equal to FE, correct? So imagine more and more electron, more and more holes flow inside. This Fe become stronger and stronger until finally Fe equal to Fb, game over. So at this point onwards, Fb is equal to Fe. And then VH is constant. Okay. So sometimes they will ask you, explain why there's a maximum value for the Hall voltage, then you can just say that the Hall voltage will increase until FB equal Fe. Although this one looks very sus, looks a lot like the velocity selector. The principles are the same. Okay. All right. Before we continue this story, I'm going to ask you to revisit your decision a bit. Previously, we decided to make this thing a P-type semiconductor. What happens when I replace it with an N-type semiconductor? Will anything change? Kecil-kecil kalau tak I put here. Will anything change? If let's say now this is a bunch of electrons. Okay, first question. What started the whole story is the magnetic force. So will the magnetic force change direction? Teacher, the current is the same. Current is the same. Magnetic field is the same. So force will stay the same? You're right. This means the direction of FB is the same. Force will stay the same. So in this case, this side will be negatively charged. So all the negative charge will gather here. Negative, negative, negative. Okay. Making the other side positive, 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 positive. So the whole scenario will happen again. The only difference is that now the yellow color side becomes negatively charged and the blue color side, the other side, becomes positively charged. So this is N-type semiconductor. So if we use N-type, the polarity of VH is reversed. Reverse the polarity. They asked before. If they ask you to explain why, then you just say the majority charge carrier is electron, electron go one side. For the first case, P-type, majority charge carrier is holes, holes go to the same side. So the direction of force doesn't change. Only thing that change is that what are you sweeping to the left? Are you sweeping the majority charge carrier, which is positive holes, to the left? Then this left side is positive. Or are you sweeping the majority charge carrier of electrons to the left? Then this side becomes negative. Then you swap polarity. Great question. Okay. So all this story, if scared forget, don't worry. Right here one. Okay. So we're going to put a thin strip of semiconductor. It's placed how should I put this? We need to put it in a certain way where it is sort of like 90 degrees. It's like 90 degrees to the magnetic field and also 90 degrees to the current. Okay, so let me pull it out. Okay. So we're going to place it perpendicular or normal to a uniform magnetic field. And then the majority charge carriers, which are electrons, for N, no wait, we choose holes. So positively charged holes for P-type semiconductor are made to flow again normal or at right angles to the magnetic field. So the first one, the conductor or the slice must be 90 degree to B. Teacher, can 90 degree here? Can. You have a 3D box what? Nah, 3D box. Can 90 degree on this face? Can 90 degree on the top face? Can 90 degree on the front face? I don't really care which face, just choose a face. Okay, face normal. Okay, then after that, we put the current. So current can be here. Current can also be here. If let's say it's the other face, it can also come. Yeah, basically 90 degree can. Yeah. I'm just going to stick to the original one. Okay, I 90 degree to B. Using Fleming's left-hand rule, a resultant force that is normal to both magnetic field direction and current will act on the holes. So the holes will be attracted to the side CFPS. I'm going to copy from the chat. Causing a charge to build up on the yellow color side. Okay, and whenever there's a charge build up, we can say there is also an electric field set up across the sides. What sides are? We have CFPS, and we also have this blue color side, which is DERQ, DERQ. This sets up a potential difference. This is our main character, our Hall voltage. Potential difference across, we like to call it the slice, or you can say across the semiconductor, known as Hall voltage. Ta-da, this is the VIP. As more and more charges accumulate, your Hall voltage will increase, and this causes the electric field strength to increase. And the charge build-up will stop when Fe is equal to Fb. So based on this, we can derive the Hall voltage equation. Fe is equal to Fb. Electric force is QE. Magnetic force is BQV. Because we very intentionally make everyone 90 degrees, so there's no sine theta here. Okay. So remember, the purpose of us doing this is still to measure our B. Okay. We need to measure our B. Well, first things first, I'm going to throw away the Q. Bye-bye. No more. And I remember from my study of electric field, this thing looks like a parallel plate, don't you think? Like you got two parallel plates like that. So the electric field that I set up, let's say I go back to the p-type semiconductor, the direction of the electric field is here, it is E. Correct? But E also happen to be equal to the Hall voltage divided by the separation between the positive and negative plate, VH over D. So I'm going to label this B here. Here to here is my B. That's a Hall voltage law. You can find the electric field by taking the value of Hall voltage and measuring the length PQ. Okay, let's do that. This is VH over D. Throw it inside. We have VH over D is equal to BV. This V happens to be the speed of my charge carrier, right? So I'm going to roughly mention here that V is the drift velocity of the charge carrier. Oftentimes it's electron, but if we decide to use holes, we can treat this like a empty space for electron. So from here, we can use the equation I is NAVQ or NAVE, AS stuff. And from here, V is equal to I over NAV. We're going to substitute inside law. Can? So I'm going to substitute this inside. Because of this, Hall voltage will now be equal to B times V I over NAE. And then this VH over D, the D I bring up, okay? So multiply by D. Okay. What is A? Which is A? Where is A? Let me try to copy the back. Where is A? Which A do we use whenever there's drift velocity? Push this here. Shrink it a bit. Okay. The direction of current is here. So based on our AS understanding of drift velocity, the area A, this area A, is this area, the area that is perpendicular or 90 degrees to the current. This is your A. But also at the same time, my friends, ladies and gentlemen, I can write A in terms of, remember this was our plate separation, D. I can write A in terms of D, and this thickness here, T. A is equal to D times T. Okay, let's put inside. VH is equal to BI over N times DT times E bracket times T. Okay, this is your area. Okay, D and D, we are doing this so that we can cancel Dungeons and Dragons. No, we can cancel the D now, okay? Eliminate the blue, use a different color. Okay, use pink. Okay, bye-bye. So in the end, we end up with the equation VH is BI over, hey, where is my, okay, my D and D cancel. NTE, I prefer NET lah, because can pronounce ma, BI over net. So there are two key steps to deriving this equation. Number one, you should be able to know that VH, the saturation VH that we're looking for, the maximum potential, happens when FE equal FB. Both forces are equal and they balance out each other. Okay, so we can then substitute E is VH over D. So the first substitution. Second substitution is the drift velocity equation. And then the third step is to actually cancel the D by using the dimensions of the semiconductor. Okay. All right. Before I move on, this equation is given to you during your exam in your formula sheet. Let me double check because they updated the formula sheet. During the syllabus refresh. Adakah dia bagi? Got Okay. So in exam, the formula will look like this. I prefer BI over net because I like things that I can pronounce. If I can pronounce, I can memorize easier. Of course, can make a song. But they use NTQ or NQP. Jalana is the same thing. Okay, E is equal to Q. Okay, so I'm going to borrow this. I'm going to borrow this, and for the sake of your note, if you are looking at this like the night before the exam or something like that, I will label everything very clearly for you. VH is hall voltage. Okay, I think B is self-explanatory. The magnetic field is B, magnetic flux density. I is the current, so I think BI is okay. But we need to talk a bit about N. What is this N again? This N is charge density. And because of the term density, N is equal to number of charge carrier per unit volume. Who knows lah, maybe they want to disturb you. So just FYI, this is your N. Okay, what is T? Pay attention. This T here, the orientation of this semiconductor can flip one. So this one is the side, the easiest way to remember is the side parallel to B. Nah, T is parallel to B, so it's this side. Or you could say, nah, current take these two phase already. So it is the phase that has something to do with the current. But I think, and then the whole voltage is across this way. But I think the easiest way to just see is parallel to B lah. Okay, and finally, as usual, your Q is equal to 1.6 times 10 to the power of negative 19. And crucially, this tells me that if I use the same semiconductor and I keep everything the same, VH is proportional to B. I can use hall voltage to measure my magnetic flux density B if I keep the other four characters constant in my experiment, which I can do because current is I sendiri letak one ma. I decide I get to control the current. Q is 1.6 times 10 to the power of negative 19. T I can measure using micrometer or a vernier caliper. And the charge density, this one, I can either calculate from the drift velocity equation, or I could even look up what is the charge density of common materials. So I can definitely find B using this equation. Okay, so a very important application here is VH is used to measure B because number one, VH is proportional to B. Okay, so we're going to look at how to do that very quickly. And not just that, we can calibrate it using a known field. I'll write all of that down separately. But VH is proportional to B. And because number two, I and T can be measured and fixed. And then number three, your N and Q are known constants. If let's say, for example, you choose silicon, then the silicon's charge carrier is the same because charge density is the same because it's number of charge carrier per unit volume. Okay. Let's try question first before we level up using the instrument. Just want to do maybe a recent one. Let's see. Also one that is not already recorded. You can watch again. We're going to do page recent years we have. I think we're going to do something a bit more recent. Because my past year only collected to May, June 20. I will update one. It's just that in my college, I don't teach this exam cohort. You lah, the A2 students. So I haven't updated more. Busy dealing with the new kids. Let's look at ON papers. By the way, right, the ON 21 papers are already out. And the questions are quite atypical. We will try them closer to your trials. So it's very hard to come by like a full paper that you can use, especially since you're at the new syllabus. So the more recent ones, especially if you want to test and see whether you are exam ready or not, I will keep to sit down and do in one sitting, just to make sure you don't have time management problem. So I think we can use the ON 20 paper from a year ago. Okay, I'll crop the question, and then I'll send you a link. Give me a sec. This is solve one. This is a complete and not complicated question because it's just the Hall effect in one single question. They didn't combine with other subtopics. ON 20, paper 4-1. 4-1. Let's paper 4-1. Okay. So spoiler alert lah, if you can avoid the ON 21 paper until before your trial, that will help you because you want to try the question first before you watch the solution. That way you know if there's any, if you are exam ready, closest to the type of paper that you expect to see in your exam. But because it's new syllabus, I don't really expect the questions to be too complicated. So I don't know lah, CIE is not very predictable. Okay, so this question is 8 marks. I'll give you 9 minutes now. Right. The only thing I want to talk about is the magnetic field is in a totally new direction. GG. Yeah. And then the electrons, the negative charge is going this direction. Electron, not current, it's electron. Where's the current? Okay, I'll let you decide. Try the question. I'll give you, we'll resume at 10 p.m. Try. You can also talk to me in the chat. I'll be here. I'll let the Zoom ladies get in. Okay, so here is a conducting material. Look, if I replace the semiconductor with a metal, you get the same Hall effect, okay? But there's a reason why we choose semiconductor, and the reason will be quite obvious to you when we do questions like this. So basically, you just treat this one as any material, okay? Where the phase QRLK normal to the uniform magnetic field of flux density B. Okay, so this phase is normal to the magnetic field. The bulk. Here is where your magnetic field is acting. And going in from this side. Electrons enter the slice traveling perpendicular to the phase PQKJ. Okay, this part. 90 degrees to this one. So for the free electrons moving in the slice, state the direction of the force on an electron due to the movement of the electron in the magnetic field. The direction of force. So we got to take out our left hand again. Let's hope you got this right. FBI. Index finger, point to the left. Okay, my webcam is flipped. I point here, but I get confused. So I'm going to point to my left. You point to your left. Okay. And then your index finger or your middle finger, stick it out. This middle finger must follow the direction of current. If your electron is pointing in this direction, then the direction of current is opposite because this is electron. Direction of current is here. This is I. So your index finger pointing to the left, turn your left hand so that your middle finger is pointing towards you or behind you, while keeping your index finger still pointing to the left. You will notice that your thumb is pointing downwards. So hopefully you got that part right. The force is acting down in this direction. Oops, this direction. This is F. This is F. This is B. And this is I. Current is here. Okay. Something like this. All right. Let me know if you need help. I'm just going to write here. Downwards. Or if you're feeling a bit paranoid, I will say towards MLKJ. Towards the face MLKJ. Okay. Identify the phases using the letters between which the potential difference is developed. Okay, sure. So if the force pulls the electrons downwards, so the electrons will all begin to gather down here. So I'm going to rub off this one because we don't need to look at it anymore. The electrons will gather down here. So this side will be full of electrons down here. And if electrons are down here, the upper phase will be positive charge. This phase will be positive charge. So your Hall voltage is actually set up between here, the top phase, to here, the bottom phase. So PSRQ. So PSRQ and the bottom phase MLKJ. Explain why the potential difference in A2 reaches a maximum value. Right. For this one, we are going to look at the forces, and it's 2 marks. So I would say as more and more charge accumulates, let me type. So make sure you mention the accumulation of charge, and also the electric force is equal to the magnetic force. Okay. And also the role of the electric field. So as more electrons or more charges accumulates on the opposing faces, PS, RQ, and MLKJ, and electric field, need to explain why the force is there in the first place. It's set up. Maximum VH or Hall voltage occurs when occurs when Fe is equal to F. The electric force on the electron is equal in magnitude but acting in opposite direction to the magnetic force, acting on the same electron. So the first thing, this part here, you are explaining the presence of the electric field. Why is there an electric field in the first place? So the whole point here is just when you get more charge, you get E field, and the E field is actually getting stronger and stronger. Okay. The second mark is when, because of E field, it justifies the presence of the electric force. And you mentioned this electric force is equal in magnitude but acting in opposite direction to the magnetic force. This will be the second mark. There's electric force, there's magnetic force. B1. Okay. So whenever you are trying to explain something, if let's say there is a force, if you can, explain why is there a force in the first place. Unless it's very obvious, like in this case, there's a magnetic force. They already mentioned here. Direction of the force due to the movement of the electron in the magnetic field. Force on the electron due to movement of electron in magnetic field is magnetic force. It's the longhand version or the nama panjang for magnetic force. So you don't really need to explain why is there magnetic force, but you should explain why is there electric force. Oh, because there's an electric field. Why is there an electric field? Because the charge will accumulate or the charge will separate. Okay. All right, next, the number of free electrons per unit volume in the slice of the material, this is N. Thickness of PQ of the slice is 0.10 mm. Let's look at PQ. PQ is here. This is PQ. And PQ is parallel to B. You can see PQ is here to here, B is like that. So good. This is our T. This is T, which is parallel to the magnetic field. The magnetic flux density is this one. Calculate the potential difference or the Hall voltage across the slice for the current, this one. So we'll just plug and play. BI over net or BI over NQT, whichever you like. So we have magnetic field. We're measuring quite a weak field, but that's okay. We have current. We also put very small current inside. N is 1.3 times 10 to the power of 29. 1.6 times 10 to the power negative 19. And thickness is 0.10 mm. So negative 3. So you throw all of this into your calculator, you will get 1.4 times 10 to the power of negative 12. This is so small. How to measure negative 12? It's 0.00000. Okay, like a lot of 0.14. So I'll make a note here. This is too small to be measured. Okay. Next one. The slice in C is a metal, you don't say. By reference to your answer in C, suggest why Hall probes are usually made using semiconductors rather than metals. So of all these 5 numbers that we substitute just now to find VH, semiconductor changes which value? BINET. Which one do you think changes when I replace it with a semiconductor? This is a metal, so this is metal. The material is metal. So if I replace with a semiconductor, which one will change? The N, correct lah, the N. Do you think the N will be bigger or smaller? N, oops. N for semiconductor, number of charge carrier per unit volume. And the N for metal. Which one is bigger? Which material have more mobile charge carrier? Very good, it's smaller. The metal has a larger number of free electron. Name is metal already, right? So in this case, we'll say that the semiconductors have a value of N much smaller than metal. Significantly smaller. Okay. And then you can say when N is small, what happens to VH? I'll write the equation here. Since VH is equal to BI over NQT or NET, when this N is small, your denominator is smaller. So your value will increase. VH for semiconductor is much larger. And a larger value, anything larger than -12 is easier to measure, okay? And easier to measure than 1.4 times 10 to the power of -12. Instead, that is too small. All right. So a standard Hall probe question will look something like this. There's not many marks. They will ask you to identify either which side, where to put the magnetic field, basically the whole drawing by twisting it, asking you to identify something about the drawing, doing a calculation and doing some explanation that should be pretty obvious by now. Okay. So we're going to use the remaining around half an hour of our time, about 35 minutes, to do a paper 5 question about this Hall probe itself. But before we move on, I want to complete the notes first. So this part, okay. There are a few things that you should also notice. I'm gonna put here. Hey. Best practice or best measures when using Hall probe. For measurable VH. Okay, number 1. We have one already. Use a semiconductor instead of metal. You write this in paper 5, is no mark lah. All Hall probes that you can find in the lab is made out of semiconductor. But just so you know, this is so that N is small. Number 2, look at the equation. What else can I do to make sure that my VH is measurable? I'm measuring B, so I shouldn't change the thing that I'm measuring, but I could make the current bigger. So use a large current in the slice of the semiconductor. The large currents are recommended. All right, number 3. We must have, okay, so this I increase. We must have teeny tiny t. Use a thin slice of semiconductor. Thin. Yeah, the rest cannot change already. You can't change E because it's 1.6. You don't want to change B because you're measuring the thing. But here are also other things to pay attention to. Number 4. When we derive this equation, we made an assumption that B is 90 degrees to the slice. But if let's say this is my Hall probe, this IKEA stupid thing is my Hall probe, and I have magnetic field. So let's say I want to measure the magnetic field of my magnet bar, north and south. So my field line is just like south is going in. So my field line is like this, right? And maybe I decided, I wonder how strong is the magnetic flux density, or how large is the magnetic flux density at a distance of 5 cm away. So here. So I'm going to take my Hall probe, which generally looks something like what I'm holding, and I'm going to stick it here. This is my Hall probe. How on earth do I make sure this Hall probe is the inside? There's a slice here. There's a tiny slice. So this is my slice of semiconductor. How do I make sure that this slice is 90 degrees to the magnetic field that I can't even see with my naked eye? So magnetic field is like shooting out in different directions. GG. How to know, teacher? If I can draw the magnetic field, I'm Superman. Okay. We don't know the direction of the magnetic field, but what we can do is we can turn this thing. So imagine this is your Hall probe, and I connect to a Hall, to a device, to a CRO or a sensitive voltmeter to measure the Hall voltage. What I could do is I could turn until the Hall voltage reading is maximum. Okay. So if let's say this is my slice, I'm gonna draw it this way. So if the field is like this is maximum reading. So what I will do is I will rotate the Hall probe. So step number 4 that you can write, so this one is P5, you can write, these two you can write in P5. They can all write in P5, except the first one. Okay. So the way we do this is we will place the Hall probe at the position desired to be measured. And rotate until VH is maximum. After that it's okay. You can clamp it in place. Then clamp in place. So you don't move anything already. You don't move the magnet. You don't move the Hall probe. You just put it there. That's it. Okay. So we will rotate this. In fact, if you want, roughly your VH against theta, I think there's a question. We'll do a question regarding this later. Will look something, I don't know, it will increase to a maximum and then it will decrease. May not be sign, it just may be increase, decrease. So this one kind of shows you that it is maximum. Actually, it can increase, decrease to flip the other side, depending on the orientation, because you don't change the direction of the current. This slice here is a simplified drawing of this one. We can't change the direction of the current. So as we rotate, the magnetic field will pass through different phases. So sometimes the polarity will flip. So basically, this one will change. I need more detail. Maybe don't draw. Later we confuse. Refer to customers. Okay, so rotate until you get maximum reading, and then you clamp it in place. This one is to make sure that B is 90 degrees to the slice. And finally, another thing that you can do for your Hall probe number 5 is to calibrate it. Calibrate the Hall probe with a known field. The last time we encountered the word calibrate is thermometer. So let's recall a bit about what we did for a thermometer. When we calibrate the thermometer with a known temperature called a fixed point. So the known temperature we had was 0 degrees Celsius and 100 degrees Celsius. Remember this? Okay, so we're going to repeat the procedure again for the Hall probe. For the Hall probe, what we are doing is we know the field. How do we know? Maybe I set up a wire here like that. And then I place the Hall probe here, here, here at different value of R. I can measure and adjust the current. B is equal to mu naught I over 2 pi R. So I put a distance R1, I have VH1. I put a distance R2, I have VH2. I put a distance R3, I have VH3. So when I plot a graph of B against VH, because at R1, I will have B1, R2, I have B2, R3, I have B3. I will get a graph that looks something like this one. In fact, it will pass through the origin. Here is B3, here is B2, here is B1. R3, R2, R1. So if I take enough data based on the field that I already know, then I can just draw a graph of best fit line. No? Then I take this Hall probe and I go and measure my magnet bar. My magnet bar gives me reading of, I don't know. Sorry, not R1, R2, R3, my bad. VH1, VH2, VH3. VH3, VH2, this is VH1. Stronger field closer to the wire. So I can measure this just based on the position. So if I already know the field, I can use this equation to calculate B. Because it's just a matter of measuring I and R. Now, once I have I and R, I know my value of B. So I know the value of B at different positions. Then I take my Hall probe, connect to a voltmeter. Using that voltmeter, I can have 3 different readings. No. And then I plot graph. Of course, we take more than 3, but the idea is the same. But in paper 5, you just need to write this sentence. But if you intend to do more science, calibration is an important skill that you should have. Meaning I have this device. I need to check and make sure it can measure what I want it to measure predictably. So I calibrate. If you're doing bio, a control set is a calibration step. If you buy crypto, you can calibrate your Excel sheet to the market. If you buy crypto. Not me, no time. Too many things to mark. The Ch20 life. Okay, so we're gonna try and include this in an experiment, but this is just the best practice. Do you need to know all? No need lah. You write 2 or 3, you can get marks on it. That's all. Right, we're gonna look at the paper from Feb March. So I think the last time Hall probe came out was Feb March 20. Good game. So I'll print it out for you. I send the paper file one into the book already. I mean, into the chat. Oh, there's a lawn here. We may want to try this paper. Oh, capacitor, much interesting. Okay, do try it. Try it. If you want to, you can send to me on Discord. I will mark. Just saying. Okay, let's look at this question. Here we have a magnet bar and a spring. It doesn't look too intimidating. Looks pretty okay, right? And it says here that it is the student investigate how the induced EMF E in the coil placed below the magnet depends on X. Okay, so this one, we are actually not really measuring B. Beyond the fact that this B is actually it's a constant. Because they want the relationship of E and X. I want to find a question where your B is your main character. Your watak utama. This one is watak sampingan. So kejap. I want to find the one where it is a main character. Couldn't find it. Inside. Take it from my OneNote archives. Yes, this one. Okay. We're gonna do, yeah. This one you want to do, you can do. You can try question 2 if you want to, amongst the other questions that you should do. But I would like to do one where the main character is the Hall probe. Okay. So this is in my set B handout. If you want to know where the paper 5 handouts are, they are in here. Paper 5. Set B. Okay. If you feel that there are certain things that you feel like you want to practice, you can open up wrong file. You can open up the set A part 1. Basically, what I wrote about the Hall probe is all here. There. Okay. And then all the years where Hall probe came out is here. Some they are the main character, some they are the secondary character. But today we want to help it be the main character. And if you are free, you don't know what to do for paper 5, you just go and see, I don't know how to measure angle. You go and try these 2 questions. Something like that. Okay. Everything is listed out already. And yes, they can ask other stuff, but let's focus on this one. So this student is going to use the Hall probe to investigate the magnetic flux density due to a U-shaped electromagnet as shown in figure 1.1. Let me, for those friends who are tableting their way, I'm not sure if any of you are. Let me send you a link to the paper. One hot second. ON 16 paper 5.2. Okay. Thank you. Paper.sc to the rescue. Okay, so this question, we're going to use a Hall probe to investigate the magnetic flux density B due to the U-shaped electromagnet. And here is the basic setup. If paper 5, they give you a diagram, it's very nice. You just add to the diagram. If they didn't give you a diagram, you need to draw from scratch. P is equal distance from the pole of the electromagnet. And distance P is the vertical distance between P and top of the electromagnet. I see this, or my brain think I need to explain how to measure. Because this distance is like in the middle. Do I know where to start measuring? Not really. Do I know where to stop measuring? Also not really. So I probably need to have some kind of either marker, okay, fiducial marker, if you remember this term, and set square. So you can make mental notes like this as you read the question. Now look at this B just floating there. It is suggested that the relationship between B and P, so the reason why I chose this question is because I want B to be one of the main variables. Okay, it's given by this equation, where N is the number of turn of coil, and I is the current, and alpha and K is constant. As usual, all paper 5 questions will have two things you need to do. First purpose is to test the relationship between B and P, between your variables. So that means test this relationship. Explain how your result could be used to determine values of alpha and K. So this is the second objective. You should draw a diagram and write the experiment, basically. Okay, so since I like to do this because I don't know about you, but I'm the kind of potato that will have a variable that maybe got like 3 marks, but I totally forgotten I need to write something about the variable, then GG. So I look at all these alphabet, or I list down already. I got B, I got P, which are my main variables. And then the done line, watak sampingan that I don't want to put on my movie poster will be N, I. And we also need to find alpha and K. Alpha and K. So B, K, N, I, alpha, P. Okay, everything is inside already. All right. So normally I would think about how to measure. So experiment must have instrument. Of course, since we already talk about B being our main character, this is our Hall probe. I remember the 5 points I read about the Hall probe, the final 4 points can be written one. So if you're scared, you forget, you mention rotate, large current, etc., etc. Okay, P. Just now P, I sort of mentioned that we ought to use. So I'm going to put the instrument here. And then I put any extra points that I would like to mention. Okay, so for P, it is the distance on top of the U-shaped magnet. So I probably need set square, maybe some marker. And what do I use to measure P? It is a distance, so I could use a meter rule. Okay, N. These two must be kept constant. And hopefully it's very obvious which one is your manipulator, which one is your responding. You cannot change the property of B. How do you change? You got Superman, super magic, you can change B, cannot. The only thing you can change is the distance. Okay, so in CIE, we don't talk about manipulated, we talk about independent. If you don't like the word independent variable, you can also say vary. Of course, you vary P by adjusting the location where you put the Hall probe. So you place the Hall probe at point P because you want to measure the magnetic flux density B at point P. So this is independent, or we vary this. And then B is your dependent. Dependent, or in other words, we will call this measure. So you can always write vary P and then measure B. It has the same meaning if you're lazy, less words. Okay, so these two keep constant, but okay, N can be kept constant if we use the same coil. So I probably will not write this, but I think, okay, maybe I'll ask you, do you think N should be big? I should have a lot of turns, or I should have little turns, tiny turns? What would you suggest? Will you suggest that n be large or small? For optimum measurement, for measurable B, do we think we need a lot of turns or little turns? Large, very good. We need large N for large B. Benda yang besar senang diukur. Correct or not? Very big, easy. Not easy lah, but you get my point. If I can see it, I can measure it. But if it's too small, maybe cannot detect. So large B. Okay, so this one must be constant. How to keep constant? We probably need an ammeter, and we probably need a variable resistor. That means I need to draw a circuit diagram. If not, then the current come from where? Whenever I see I my brain thing draw circuit already. Okay, so I also want I to be large for the same reason. I want the B to be strong. Big N, big I, look at the equation, means big B. Okay, these two calculate one ma. So this one is to determine. So we're going to come out with an equation. Since we're all quite competent in maths, I will leave it to the very end. We can write it out. We can write now already. So I'm gonna screenshot this and just put it aside so we can write maybe here. But before that, I want to draw the drawing. So I'll bring it in a bit later. But what I mean by if they give you this, you get a free pass is because we can copy the drawing. Since we all come from SPM, you have done this before in paper 3. This is even better. You don't have to write hypothesis, inference, materials, all that no need to write. You just need to look at this and go like, I'm going to copy this. Okay, can copy the whole thing. Of course, I am cheating a bit lah. I'm the teacher ma. I can print screen. During exam, you cannot print screen, okay? I'll draw a table because a table makes it a bit easier for me. And then I will think. First thing, easiest to draw is to complete the circuit. I want to make sure that this current I is constant. So I sambung, I put a power supply. Now one large current, so I dot, I draw many power supply. And then I have with me a variable resistor in case the coil heats up. Oh, wait a minute. The coil will heat up. Current large. So here you can talk about safety. Yeah, later we just remember to mention. How do we keep the current constant? Obviously, we need an ammeter. Otherwise, what on earth are we doing? Okay, done. So the current side already settled. And then this is coil. During exam, I will also say coil of n turns. And just to label my diagram, I will put power supply here. I think rheostat or variable resistor and ammeter no need to label lah, because they are common circuit symbols. Okay. All right. So we're done with this first part, the circuit drawing. Okay. What to include in your diagram? We need the table. So you look at all these purple color thing. I should see them in the diagram because they're instruments, ma. Where to put the instrument? How to set up the instrument? That's why we have this table. Okay, let's think about the Hall probe. You want to measure the magnetic field here. So I'm going to draw my Hall probe like this. But whenever you draw something floating, layang in the middle of the air, don't leave it like that. Teacher, this ammeter not layang. No, if you draw circuit drawing out, I know all your circuit component is on the table already. If you feel that you have a lot of free time, then by all means draw a 3D ammeter on the table here lah. So circuit diagram is the only exception, but everything else cannot float. Okay, so teacher, I don't know how to draw a Hall probe. You draw like that can already, because they draw like that in your syllabus. I show you how they draw now in your past year questions if you have done some of them. They draw it something like this. Wait, I caught for you. If you look at past year questions, even in the nice 3D drawing, their hall probe is drawn this way. I follow only. CIE draw like this. I also draw like this one. Okay. So I'm going to draw a hall probe. But obviously, this hall probe needs to be connected. And what are we measuring? The hall voltage. So I will connect this to a voltmeter. Teacher, the current, the current is part of the hall probe. It's already inside. No need to draw a separate circuit. But please label hall probe. I said just now, cannot layang. So your hall probe cannot just chill there in the mid-air. Somebody need to support it. We are all a bit better if we have a support system. Kawan can support you, right? So a support system is a retort stand. But you see, I think ahead. I also need to measure P. So I should also probably have a ruler. Okay, I draw the ruler also. Okay, we draw the ruler. We have to measure from the level of this thing. Okay. So I'm going to draw a ruler so that it's longer, something like this. And then I continue. Okay, maybe it's a bit too close. Hang on. I need to draw the clamp. Need space for the clamp. And maybe something like this. So that I can measure the distance of P. Okay. This is my clamp. Maybe I should measure from the ground, right? So, if you think ahead, well, probably bigger. If not, then when you write halfway, you notice maybe I should measure from the ground, then you just erase and draw in. I'll measure from the ground, or rather I'll measure from the table. Okay. This thing also cannot float, so draw a retort stand. Teacher can clamp together on the same retort stand. Can clamp on two different retort stand. Can. Got clamp can already. I'm drawing it in strict XPM style where I lorate all the clamp portion, but physics is not very strict. But I make sure I label. Okay, so label everything. This is hall probe. This one is clamp. Meter rule. More clamp. Retort stand. Please label the iron core also, okay? Don't forget this one. Okay, we draw the ruler already. We draw the hall probe. Okay lah, I think we're good. Can start now. You okay so far? All right. So this is an alternate one that I drew on my own. I think it looks the same. It's almost the same. But if you tak ada tempat nak retort stand, then you can retort stand kiri kanan. Okay. Now this is the kiri kanan version. One side here, one side here. You just find a place to squeeze it in now. I find it easier to draw it in place than draw out the retort stand to the side. Label everything. This one I draw on paper, hand draw. Okay. A few things that we need to concern ourselves with is P. So when you measure P, maybe I measure this distance to the top of the iron core. Let's say I call this H1. Easy to measure, I have a iron core here. And then I go and measure from here to the position of the hall probe. Here to here is H2. And then I write P is H2 minus H1. Okay. So what to write? You draw the diagram already, right? So we think of the 4-letter or 4 alphabet P, M, A, D. So statement of problem, method to measure, analysis. And this is called dan lain-lain. Dan lain-lain, no, like extra additional details. Dan lain-lain. Okay. So we're going to start with statement of problem. Okay, or defining the problem. You don't write header also, never mind. It's just to guide your brain only. So you can either say vary P and measure B, or you could say independent variable colon P, where P is lowercase p. Okay. Dependent variable is your B. Magnetic flux density. Do you need to write the full name? Nope, unless you want to. But don't forget your constant variables. So it's your number of turns, you use the same coil, and the current in the coil. Or you could say measure vary P and measure B, comma, heat N and I constant. This one is the tulisan orang malas, not malas. The man of less words. They are both okay. So there are 2 marks here. If you mention your variables correctly, you get 1 mark, P1. Okay? Or this one. Whatever lah, whichever lah. And then you keep N and I constant. This is P1. Or constant variable, this one is P. Okay. Once you're done with statement of problem, we can then move on to method. Method includes diagram. And diagram. You don't write the N diagram also, never mind. Okay, so apparatus as drawn is set up. So what do I look for in the diagram? I write here already. Got hall probe, got ruler, got stand, and we need to support them with support. So these 2, hall probe and ruler, must have support. The support that I use is a retort stand now. CIE also accept G clamp, but macam mana korang nak G clamp the hall probe? How to G clamp? I don't know. Because the masking is like accept reasonable support, e.g. retort stand and G clamp. I stare at the hall probe very long time. How to G clamp the hall probe? Okay, I also don't know. Okay, we retort stand everything. If it's floating, retort stand. If you want to put it on the table, G clamp. Okay, anyway, number 1. 2 marks are here. 1 mark if you have hall probe, ruler, and a support system. 2nd mark is the circuit. Okay, we should label the circuit here is plus label of coil and soft iron core. So if you didn't label these 2 like me, then label the coil, then you will lose 1 mark because I don't know what you are connecting to. Okay, this circuit needs to have a power supply, an ammeter, a resistor, a coil, and a soft iron core. Then you get this mark. So we don't ask you to list down the instrument because can tell from the diagram, no need to list lah. All right. Okay, method. Once we have all of this in place, we can now go back to our beautiful table. Put it at the side so we don't mix out certain things. So we have the hall probe, we have this one. So now we need to talk about how to measure. We vary P, right? So we first talk about measuring P first. So measure P using a ruler. This is the first mark. But we can have more values, right? Okay. So to determine P, take the distance. Take the distance between the bench top or the table above bench to the top of electromagnet H1. So my H1 is here, from the bench to the electromagnet, and from the bench to the Hall probe at point P. H1. And the distance between the height above bench to the position of the Hall probe at point P, H2. So lowercase p is equal to H2 minus H1. Okay, that's point number 1. So if you measure P using ruler, this is M1 already. And then you have a way to find P, like you say, take distance. You can use your own label. Basically, as an examiner, I will have to read this. And if I understand that you measure P by using a method that I can accept, meaning you don't measure the distance from one floating point to another floating point. Okay. You measure actually from the table to the electromagnet, from the table to the Hall probe. Things that you can see. You can't just measure a point from here to a point from here. You need to have a marker. So if you indicate clearly the marker, which is your bench top or your table top, and then here, and then you draw on your diagram, even if you feel that your sentence a bit chacat, but you label nicely on the diagram, you'll probably get the mark. They're quite lenient. Okay. All right. Next. What else? This P, I kind of need to make sure that I measure all this reading as 90 degrees, right? So I would say use set square. Actually, not fiducial marker, it's called plumb line. But I use set square more lah. Or plumb line to ensure that all measurement of H1 and H2 are parallel and perpendicular to the table. Can now. Okay, next. We adjust P time to measure H. Hall probe is rotated. Remember, we need to rotate so we get the maximum reading. Rotated until the maximum reading of Hall voltage is obtained. Bracket. This shows that the magnetic field is perpendicular to the probe slice. You don't write the bracket also can, never mind. I'm just writing it for you. Okay. So clamp the Hall probe in place. And the reading of VH of the voltmeter is taken. Okay, finish already. We're going to repeat the experiment by putting a new P, right? But before we use a new P, we need to repeat the experiment. So for each value of P, the experiment is repeated and the Hall probe reading is taken and averaged. Okay, experiment repeated by reversing the current. This part is important. For magnets, we reverse the current. If you have done some magnet experiment for paper 3, I've forgotten, were you exempted from paper 3? Anyway, we like to flip the pole just to double confirm that the field is the same. So we always reverse the pole of the magnet, or we reverse the current. Okay, but this reversing current is only for B. And when you talk about this repeat thing, always say for each value of your independent variable, P, experiment is repeated, and the dependent variable in this case is the Hall probe or the reading of B, taken and average. These points must be there. Okay, the reversing the current part is a Hall probe thing or a magnetic field thing. Okay. Anything else? Nothing. We can just, if you feel like just finishing and read the experiment, although this point here got no mark, you can say that for the same P, or the experiment repeats, for different values of P. Okay, so method is done. We move on to analysis. So to do analysis, I need to copy the equation. And the equation is this one. Okay, I copy one. I'm going to throw this aside. Linear graph only. I put in brackets so you remember. In physics, we only accept straight graphs. If not straight, we cannot do any analysis. Not much lah. So to linearize this graph, I will ln both sides. Hopefully this is not new to you. Kni E negative alpha P. Ln B is equal to ln, all the constant I take out. Kni, this is multiply, so it's actually plus ln E negative alpha P. So this is A, this is B. I'm using the identity ln AB is ln A plus ln B. After I take ln on both sides. Okay. So now I will have ln B is equal to ln E is 1. So it's negative alpha P plus ln Kni. For those of you who learn a bit bakarat already, negative alpha P, I can bring the alpha P down. This is ln E. This thing is 1. So I get alpha P. It's the same thing. Okay, now, what graph to plot? We can say plot a graph of, so number 1, analysis, plot a graph of ln B against P. Number 2, remember we got 2 objectives. Here is where we relate to the objective of the, or the purpose of the experiment. First one is to determine the relationship. So I would say that the suggested relationship, this equation, B is equal to Kni E to the power negative alpha P, is valid if the graph that I just suggested to plot in 1 is a straight line. Does it have a y-intercept? Yes. Y is equal to mx plus c. So this is your y-axis. This is your x-axis. So the relationship is valid if graph is a straight line with a y-intercept. Okay. Point number 3. We need to find alpha and k. So I can see here that gradient is equal to negative alpha. Don't leave your answer like this. Alpha is equal to negative gradient. okay? And y-intercept is equal to ln k and I. I'm looking for k. So e to the power of y-intercept, you want to call it c also can, but I'll just keep it this way because I'm not going to use it anymore after that, is equal to k and I. So k will be equal to e to the power of y-intercept divided by ni. So we must write the equation with the unknown that they want you to find as the subject of your equation. Alpha and k must be subject of the equation. You don't want to write gradient here, you can put comma m, and then this you can just delete the whole thing and write negative m. Can also, but I'm not going to use it anymore, so I wouldn't bother. In case there's m inside the equation, then I need to head it and come up with another symbol. This is fine. Okay. If you leave your answer like this, you will get 0 mark. Easy. You assume that the person reading your lab report is like a mathematics potato. So mathematics potato don't know how to move negative sign. Cannot. It's like computer writing code. Computer don't know. Computer only know how to run this code. All right. Okay, analysis done. And then halfway, you're like additional detail. Teacher, I got a lot of things I didn't write yet, like safety, right here. To prevent, do not touch the coil because it can be very hot. Or wear safety heat-proof glove. Do not touch the coil, hot coil, / wear heat-proof glove. Whenever you say there is a safety precaution, please explain what is the safety precaution. So for example, wear heat-proof glove because the coil is hot, something like that lah. Okay, we talk about large values, so use large N and I to increase E so that it is measurable. What else we didn't write? We could say that, the calibrate thing. Calibrate anything at all. Teacher, measure P using ruler can write here. Can. If you write here, I have to give you mark. So calibrate Hall probe. Calibrate is 1L. Using a known P. It's not all got marks on. Standard. And finally, I need to make sure that the Hall probe is at the middle, because point P is in the middle of your U-shaped magnet. So to ensure that P is at the midpoint, ruler and set square is used, and the plumb line is tied in the middle as a marker. The midpoint of the electromagnet. Okay, this is more than 15 marks already. Okay, I'll mark it for you. So we have done the P1 and P2, and I'll print out the whole thing, so don't worry too much about copying. The M mark is already done. So this P mark maximum can score is 2 out of 2. This M mark was 4 out of 4. Analysis is 3 out of 3. So where are your 3 marks for analysis? If the graph suggested is correct, you get A1. You suggest I plot a graph of this against that. And then what is the main thing you need to do? You need to find alpha and k. So if you have an equation with alpha correct, you get A1. The equation for k correct, you get A1. Okay. then this suggested relationship is valid if the graph is a straight line without y-intercept. This is additional detail number 1. Okay, additional detail number 2, number 3, number 4, number 5. There are some additional detail here as well. Rotated until maximum reading. Number 6. Reverse the current. Number 7. You write the right linearizing equation, which is mainly this format. Number 8. Okay. That's it. So maximum you can score is 8 marks, but we don't need 8. This is already 9. So you just need 6 out of 8. So some things you don't write also never mind. Okay, lor. That's it. The set square and plumb line thing, students often don't understand what I'm talking about. So what we'll do is we will take a set square here. And then we'll take a set square and put here. And you make sure lah, this reading and this reading summer. And then you tie a plumb line to your retort stand. And then you introduce the Hall probe. You can imagine, you take set square number 1, take set square number 2, or adjust lah until the reading here the same. This retort stand is already there, waiting. This retort stand is waiting. Here, this one is waiting for you to tie something on it. Just don't, yeah, just waiting there lah. Retort stand is, why can't I highlight color? Okay, so we will tie the plumb line, this plumb line on the retort stand. And then you don't touch anymore. Then you clamp the Hall probe on it at the plumb line. Cool. But you don't have to explain any of this. You just say use a plumb line and set square and a ruler. For set square here, got ruler reading. Hopefully. If not, then you bring your ruler in and the tatla ruler like that. Okay. To ensure that you are at the midpoint. And then hang a plumb line. These are just additional details here. Okay. So that's it. This is how you use a Hall probe. But it'll be very daunting if you haven't seen a Hall probe before. And that's what we learned today. I'll give you a list of questions to try, not so much paper 5, because once you know, it's just about knowing what to write. But questions from paper 4, especially the rotating kind of questions. Miss Ellie and I have already recorded some. You can refer to those in your own time. We are done with magnetic fields. This is a very long chapter, by the way. The first half of this topic. A note for you, the compare part, I will probably do a bit later as revision, but this MRI is not in your syllabus. Recently taken out. You are the first batch that's sitting a new syllabus, so don't study MRI. We finished magnets already. All this cool stuff, we will leave it in medical physics. Okay, so we finished the first half of magnetic fields, which is how magnetic force creates different things. So think about how we have done all of this. Force as an effect of magnetic field and current, or magnetic field and moving charge, and we have all of this. So this was our main character. We studied this, and then we looked through different things. In the next chapter, our main character will shift from force to current. These two will change place. If magnetic field can create a force with current, can magnetic field and force create a current? The answer is yes lah. That will be the second half of the chapter. Okay, go try Hall probe. If can, make sure you at least do 1 or 2 examples from all of this. In the handout, I will tamba here lah, and I'll just print it out again. Okay, that's all. Today we overtime now. Hopefully you're not too sleepy. Thank you. I'll see you next week. Stay sane.
Thank
Good
you,
night.
Miss Lee.
Good night.
Thank you, Miss Lee. Good